Right, let's see how we can solve this quiz. So the question is, are these systems laminar or turbulent? Well, how do you determine that? Basically, you look at the Reynolds number of the systems, which equals density of the fluid divided by viscosity of the fluid times velocity of the fluid times the scale of the system. And then you look, is this bigger than or smaller of the transitional Reynolds number, which is about 2000. So the only thing we have to do is just estimate this. Let's have a look. For a person drawing sucking a cocktail, these are very practical exercises. I've never solved this myself, so it's the first time I'm going to do it. And I'm just going to, you're supposed to, you're going to be engineers next year, so you're supposed to be able to handle this kind of real life questions without too much problem. So for a cocktail, the density of a cocktail is about the same density as water, so rho equals 1000, that is kilogram per cubic meter. The viscosity of a water-like liquid is in the magnitude order 10 to the minus 3. And that is square meter per second, I think. I'm not sure about this. You have to check up the dimensions of the viscosity because I'm not 100% sure. Velocity. How fast, if you suck a cocktail, how fast does it go? Well, if I suck in a bubble, it would take about maybe 1 second to do 20 centimeters. So 20 centimeters per second, that is 0.2 meter per second. And the system size, L, of a fluidic system, typically we're going to take the diameter of the system. And the diameter of a cocktail straw is what? 3 millimeter. So if I now calculate this, I get Reynolds number equals 10 to the power 3 divided by 10 to the minus 3. It gives me 10 to the power 6 times 0.2 times 3 times 10 to the minus 3 equals 0.6 times 10 to the minus 3 equals 600. Okay, so this is below 2000. So we can say it's laminar, but we see it's actually rather close to 2000. So it's borderline, but we could still say it's a laminar system. Okay. The next question was the flow through the heart. I have then we talk about blood. The density of blood is similar to that of water, 10 to the power 3. The viscosity of blood, it's going to be a bit higher. I don't know how much, say 3 times that of water. Velocity of the heart, of the blood flow in the heart, how much would that be? Well, say my heart, say that is, how big would that be? That's like a pint, small pint, and it pumps, say, 1 time a second, and a pint is, say, 2 deciliters. So I know that my volumetric flow is about 2 deciliters, so it's 0.2 liter per second. And so that flow goes to a vein, an area with an area of maybe, well, say that it has I have an aorta of 2 centimeter diameter. Then that would be an area of roughly 3 square centimeter. 3 square centimeters, 3 to the minus 4 cube square meter. So I know the volumetric flow and the area for incompressible flow. Then I know that the velocity, I know that A times U equals Q. So I know U equals Q over A. The flow per area is about, and you can calculate that. You can do the same with the length scale L will be about 2 centimeters in the side, so you can calculate the same value. Now I see actually that I made a mistake here. You see, if we look here, oh no, sorry, I didn't make a mistake. Sorry. But still, I can see my Q here is liter per second. I have to convert that to cubic meter per second, and with that I can calculate actually what my Reynolds number is. I'll see if it's more or less than 2000. For the fluid, I'm not going to have a liquid, I'm going to have a gas flow, of course. Density of a gas, typically air, 2 kilogram per cubic meter. Viscosity of gas is typically in a magnitude of 10 to the minus fifth in SI units. Now again, what is the speed with which I blow? How fast do I blow? Say maybe 1 meter per second. And the length or the diameter of my fluid is, say, also 2 centimeters. Based on this, I will be able to calculate here that I have a Reynolds number. That's actually going to be, now I get a much less viscous fluid and a much less viscous and a much lower density. So I'm going to get something different than actually I get here. So this is going to be 2 divided to 10 to the minus fifth times 1 meter per second times 2 to the minus 2. And I can estimate it's going to be around 4 times 10 to the power 3 equals 4000. So I was going to see my fluid, actually I'm going to have a slightly turbulent flow. And I think that my 1 meter per second airflow is a bit of an underestimation. I think actually you blow out faster. So typically you're going to have probably a turbulent flow. So this is how you solve this kind of exercise.